Thanks, Patrick, for the presentation. So we want to present some of our research where we're trying to pave the way for prediction of modulatory ligands activity in synaptic receptors. Well, let's start from just a reminder on the synaptic receptors. So looking at the example of glycine receptor, we do know that they are membrane proteins, and many of them are pentameric ligand-gated ion channels. And so the pore through which ion current is flowing and which constitutes the neurotransmission in our brain. So this pore, it can be closed, it can be open, and this equilibrium can be shifted depending on the agonist binding. And so the main goal of our research is to prove the extended version of mono-Weyman-Changeau model, which basically states that you can access the real pharmacological properties of the modulators, such as efficacies, which are in this case of synaptic receptors are measured as maximum open probabilities, through the binding free energies towards the open versus towards the closed states of the receptor. But the problem here is that in synaptic receptors, there are no available binding free energies directly measured experimentally for separately open and closed states. So we don't have this kind of experimental technique. We only have activities to measure. And therefore, so to prove this kind of concept, we need to have a tool which can access these binding free energies. And since we don't have any experimental approaches, we do need to use computations. The most obvious approach would be binding free energy calculations based on molecular dynamics. However, so these calculations, they are a tool, and they are not directly experimental tool. These are computations. And so, first of all, one has to understand whether this tool is applicable in the first place for the systems under interest. And so we know that the binding free energy calculations, they have two pillars, basically two problems, which can affect their adequacy to be applied to any kind of problem, which is, first of all, parameterization, or how well are your interactions described, and convergence, or how well is your phase space sampled and whether you have reproducible results. In this case, considering that kind of two different problems, we do separate our research in two parts, which is first part, so I named it delving into glycine receptors binding site with QMMM. It is related to parameterization. And so what we have observed when we were trying to start our molecular dynamic simulations in glycine receptor, and you need to do them if you want to access binding free energies towards the open or closed state, is that irrespective of the state, with different ligands, so with glycine or with taurine, glycine is a full agonist, taurine is a partial agonist. When you start classical MD simulations, the ligands change their binding poses. And it happens immediately, so either during the minimization or during the first picosecond of your simulation. So for example, glycine, it reorients its carboxyl oxygens from orthogonal direction with respect to nitrogens of arginine towards the more parallel position. And taurine, for example, changes its conformation from manti into gauche. And the problem here is twofold, because we do know that classical force fields, on one hand, they may have difficulties in describing cation-pi interactions, and cation-pi interactions are essential for synaptic receptors. But on the other hand, when we work with currently available cryo-EM structures, the Q scores, which are measuring the quality of how a given species, let's say a residue or a ligand, are fit into the electron density maps, they are also suboptimal. And so we don't know who is right, who is wrong, whether it's cryo-EM structures or whether these are our force fields. And if our force fields are inadequate, then we cannot use them to try to prove extended mono-Weyman-Changeau theory in the first place. So this change is robust with respect to change in classical force fields. So we try different classical force fields, different starting structures. It's always the same. And so because of that, we have started the collaboration with Jülich Forschungszentrum, also a part of the ALLODD, to try to run QMMM MD simulations, which would constitute annealing, equilibration of 1 picosecond, and production of 5 picoseconds. So again, these tiny time scales, they would be enough. We have proven that on the classical level, that they would be enough to see whether the same changes are observed or not. So basically what we do now is that we are equilibrating our structures on a classical level, starting from cryo-EM, but with binding sites restrained to cryo-EM. So then we choose statistically representative snapshots to start QMMM simulations with. And by statistically representative, I only mean water invasions in the binding sites, because everything else is restrained. And then we run QMMM simulations in several replicas. And then our question here is whether we will observe the same changes as we observe in classical MD simulations. And so when a reliable binding pose will be found on QMMM level, it will either support cryo-EM structures and refute the classical force fields, or vice versa. And so we are using decent QM part of more than 160 atoms, big MM part of 170,000 atoms. Those of you who are doing molecular dynamics simulations, you can see the time scales, the speeds. So 2 picoseconds per day on 25 nodes, but that's enough for us. And we are starting from various cryo-EM structures. So for lesson, we have used 2 cryo-EM structures to start. For Thorium, only 1, but that's because only 1 set of authors deposited anything with Thorium. And we use 2 snapshots per system, which are trying to capture different amount of waters in the binding site. And so already, from the results, we have run 3 out of 6 systems. So 1 snapshot with Thorium and 2 snapshots with glycine. In all of them, they agree extremely well with classical MD and not with cryo-EM. Which, first of all, is optimistic. So it says that probably, at least in terms of capture and adequate binding poses, the current classical force fields could be enough. And at the same time, it demonstrates how QMMM's MD simulations can be used as a tool to improve the resolution of cryo-EM structures when you have suboptimal Q scores. And so moving to another part of our research, which is the issue with convergence, or how well the system behavior is sampled. Here we will be working with binding free energy calculations, but not on the receptor as a target, but on acetylcholine binding protein. So again, as I mentioned, for receptors, we don't have directly measured binding free energies. However, acetylcholine binding protein, we are really lucky that this kind of target exists. It's almost a copy of extracellular domain of nicotinic acetylcholine receptor. It hosts similar cation-pi interactions. And at the same time, it has a wide range of directly measured experimental binding free energies. And so what we are doing, we have considered in the beginning, so we decided to consider 6 pharmacologically relevant compounds. They're all charged. They're all binders of acetylcholine binding protein. The range of their binding free energies is more than 5 kilocal per mole. And we are running basically absolute binding free energy calculations with around 500 nanoseconds per replica, so the sampling should be adequate. We also, I'd like to note for those of you who somewhat knows this system, that we also restrain the C loop, which is notoriously very labile, and we also have proven that it's not a big bias, so energetically it's adequate to restrain it. But here are our results. So we have run 9 replicas, because current state of the art says that in ABFE calculations, you need to be very, you need to have an ensemble approach to be robust. But you can see that in terms of absolute unsigned, in terms of average unsigned error for among these 9 replicas, for some of the ligands, we had insane deviation from the experiment. So epibutidine had 7 kilocal per mole from the experiment. And standard deviations there were also not reached on an adequate level. So more than 2 kilocal per mole for many ligands. Of course, we had no correlation. And so the fresh results is that we have tried to use, we focused on this epibutidine because 7 kilocal per mole was really strange. We have analyzed visually the binding site. The ligand really changes its binding pose from time to time. This may be the reason of this big deviation. But we have spent several months on trying different ways to run our calculations on a better way. So we have used the Hamiltonian replica exchange to enhance the sampling. And very important, we decided, because when you run these simulations, you run pentamer. And you run at the same time 5 binding sites during your equilibration stage, and then you can choose for which you would like to calculate binding free energy. So we decided to choose the most stable one to proceed with binding free energies after the equilibration. We also increased the VBA restraints to keep the ligand in this binding site, in this lucky binding site, I would say. And we also use now double annihilation instead of double decoupling to prevent kinetic traps in the bound state. And so this gave us adequate results. Epibutidine now, so only 2 kilocalories per mole difference from the experiment, and standard deviation within 1 kilocalories per mole almost. So we are really encouraged, and we want to run these calculations very soon with another ligands and see how it goes. For nicotine, it already worked well, but we need to test the other ones. And so last thing, so to recapitulate, there were 2 parts of research. One, which is QMMMD, shows that there are no indications that classical force fields are inadequate to work with synaptic receptors. And in terms of ABFO not still-blind binding protein, which is the second part, we are trying to reach control and adequate accuracy. And we have indications that this is possible. So when all that is done, we will be able to confidently proceed with extended mono-Wyman changeover model proof. Thank you very much for the attention.
Quick questions? Yeah. Okay. Very much for the presentation. There is something I'm not 100% sure to understand. The first part of your presentation basically shows that you can go with the NP. In the second part, at some point, you restrict to the calculations that to only one stable operation, which might look like perhaps it's not stable enough, so it's not productive enough. So in fact, it's contradictory with the first part. So I would like to have your comment on that.
But just to clarify, so you mean the fact that the ligand is not stable may mean that the force field is not very adequate? Yeah. So exactly. Yeah. So we were thinking about that, but it could be, of course, it could be. First of all, of course, these are 2 different targets. So glycine receptor versus nicotinic acetylcholine receptor. Unfortunately, we don't have an analog like that for glycine receptor. We only have that kind of analog, which is just a circular domain for which we have adequate experimental binding free energies only for nicotinic acetylcholine receptor. So of course that can be a factor, but hopefully, again, it can be that maybe your sampling is not enough. Maybe just 500 nanoseconds is still not enough. And if you were to run 10 times more, you would everything would integrate into something more adequate. But we are always limited in terms of sampling. So it's, of course, it's just some tricks. But the point is that if it's not you see, it's not some human-based bias, and it's a relatively objective criterion to choose the best binding pools to start calculations with. And well, I think we should first see, we should try more ligands, and if there will be just some deviations, some outliers, it may not be so critical. But yes, I mean, we don't yet know the results for a bigger data set. So we need to try, we need to see. But I think, again, so there is a deep philosophical discussion. Like, okay, you have 5 binding sites. One is stable, other are not so stable. So is the stable binding site an anomaly, or the stable binding site is actually sort of behaving correctly? And if you were to extend your calculation 10 times, all the other binding sites would be convergent to the same type of behavior. But it's always like that, I think, in molecular dynamics. But you need to know when to stop, when to sort of reiterate your large-scale calculations. So I'm sorry if the answer is vague, but I always have this feeling when I do MD that you need to exist in a little bit of a vague conditions always. But Yeah.
Thank you very much. Yes, question? So I had a couple of questions. So the analysis that led you to the, I suppose the conclusion that the classic force fields were sufficient. You said 3 or 6 systems agree. What about the other 3?
We are just, they are not yet complete. So just right now under the calculation. But so yeah, that's just this kind of insufficiency because this is still a work in progress. But yeah, so we just represent what we have right now. So yeah.
So I mean, all of this seems plausible to me, but I assume you've gone and you've taken this new protocol and run all the other cases, right? Because it certainly improves this case, so does it make anything worse?
Exactly.
You're kind of guessing with the most stable ligands.
Yeah.
Does it affect the other cases?
Yeah, again, so we have spent almost, I mean, I'm not showing everything here, but we have spent almost 6 months on trying, when we have received these results, we spent almost 6 months in discussing also with our colleagues in J&J, with colleagues from Athens. We have spent a lot of time on trying to, because to trying to understand, to improve these results. So in the end, yes, right now the fresh results are with epipatidine, and as I briefly mentioned, I don't provide it here. For nicotine, we always had very good control for nicotine. So this new approach, it sort of, there are indications it also works for nicotine, but for sure now we need to rerun not only these 6 ligands, but we have already prepared actually a data set of 20 plus ligands. And also we now have, there were some troubles with computational resources. Now we have almost unlimited computational resources. So it's, it's really, but of course, I totally agree with you. If we are unlucky, it can change. This conclusion may change, but let's maybe be optimistic because, yeah, some time was invested in that. We really hope it will work this time. So, but yeah, I clearly like tell how it is. Yeah.
So, I have a question. Okay. I have a question. Yes. A question to the key quantum mechanics of force field calculations. Maybe is it also possible, because for the amount of time to decrease a bit the atoms, because I think that this is a very big quantum mechanics field. Maybe you can decrease it, and then you have a lot of more computational power.
Sorry, decrease QM part or?
Yeah.
So we have, yeah, I agree. On the other hand, we have included entire first shell, because in this binding site, there are so many important interactions. So there are 2 phenylalanines which interact in terms of cation pi interactions. There is arginine which interacts with hydrogen bonding. There are several other residues which interact by hydrogen bonding, and there are also several phenylalanines which are farther than these 2 I've mentioned, but there are 2 more which sort of also create a cation pi cage. And what we were afraid of is that, well, imagine if we haven't taken into account some of these residues, there will always be a question, okay, maybe you have forgotten to take this residue, maybe this residue. So yeah, we just went to entire first shell. However, from what you propose, because we were considering also trying some alternative functional to prove to maybe make our result even more robust. And so if we go to more, because now we are using BLEAP, with the dispersion corrected pseudo potential, so it should correct for BLEAP inefficiency in dispersion correction, in dispersion interactions description, and dispersion interactions are important for cation pi interactions. They're just important part of them. But if we go for more costly functional, yes, your proposal may be right. If we see that it's not feasible to run too big of a, because you can imagine the scaling would be much worse. You're right. So we would opt for decreasing this binding site up to, like, the most radical decrease would be to have one modulator, arginine, and these two most crucial phenylalanines. But yeah, so we can it is possible, of course. But now it was not so needed because 2 picoseconds a day, again, for some of you, it may be an interesting speed when we compare like with hundreds nanoseconds per day in molecular dynamics. But for our approach right now, for 5 picoseconds was enough because it's enough in classical level. But you're right, we can maybe need to decrease later.
Thanks for the talk. In that slide, the conclusion, you mentioned that when all is done, you can confidently proceed with an extended and distribution of the proof. So can you clarify what is missing? You are missing the final confirmation so that you can compute the binding ranges.
Yes, so I would put it this way. So in terms of adequacy of Gleissner, of force fields in Gleissner receptor, I mean, unless these three, I mean, I'm trying to be transparent. Yeah, so at least these next three systems will give us some kind of anomalous results. I hope they will not. We are ready to go. However, there is this test of both ourselves and both method itself on whether binding free energies as a tool work on such targets. And yes, acetylcholine binding protein is not glycine receptor, but they're similar somewhat. They have this C loop, which is very removable. They have some cation pi interactions. So we need to be sure that we are capable as a team to run ABFE on these targets. And when we have proven that, then I think we will be more confident. But I mean, yes, in
Yes. Yes. Okay. Yeah. There's just one step approach from Chris Pilaris in the UK.
But yeah, so
Yeah.
we want to anyway converge on faculty and to multiple weekends for people to hear and
Yes. Thank you.
yeah, thank you.